Oh, yeah. Oh, so,
I smell this morning.
no, it's just, oh, I know that words just right there.
It's okay, we're gonna close this. Did you guys see this?
Yes. I advertised that during the SBS meeting.
Are you going to it?
Yep.
You go and you ask a question. And you tell me her response. You get extra credit.
Okay.
Because I will smile benevolently when I decide your grade on high. All right, well, I guess speaking of grades. Yeah, I'm required to make sure that you're still doing okay. So next week is check-ins. We're a little bit lagging, as I mentioned before, because of a couple missed classes. One of which is faculty's fault and one of which is weather's fault. So if you look now and you look on the Physics 5100 schedule, it should be up to date. Some of the topics are a little broad, so they're not as specific as I would wish they would be. But today we'll basically finish our discussion of statistics and data analysis to the level that you would get in this type of a class. If you are interested in any of these techniques, I don't know how many, are you both going to be here in the fall?
You're in full, yeah.
Okay, so I'm considering a special topics class. And that could be, a 1 semester class on data analysis. That could be a three unit class on general relativity. So, based on what folks are interested in, I'm going to be asking students from the department what they might be interested in taking in the fall, if they need that extra elective. Otherwise, I'll probably just do like, 2 or something, Okay, so schedule your 30-minute meeting with me. I know that you hate these, some of you love them, but this one will be reasonable. We're just gonna talk about your understanding of probability. We're gonna look at your homeworks. Hopefully you've done them by then. And then if you have thoughts on a specific topic you'd like to know more about. Questions, comments, concerns? Okay. We'll leave that up in case it looks show up a little bit later. We were talking about this population. And we had these data sets here. Let me just write them up again. Because that's the other thing I should have done this free time. Okay, so you have a population which has a person. Actually, do you have those numbers already?
Okay.
All right. Let me just write them down really quickly.
Oh, I got all.
You have all?
Yeah.
Do you have the standard deviations and everything?
The R of X, Y. The correlation.
Yeah. I don't even know if these are all like actual weights. Just read them off here. I mean, 46 and 175, that seems like really skinny and really tall.
I don't really know what kilograms well.
Well, it's like this, kilograms per 1 pound.
It's not too bad, is that?
Yeah.
Yeah, it's like 100 pounds. So it's flat. Okay, So just thinking about, you looked at the homework, right?
Mhm.
And some of you turned in the homework.
I will right now.
He's looking at me too, I also not.
I'm only looking at one person. We talked already.
Yeah.
So that's okay. So I'm looking at 50% of the class.
Oh, yeah.
And and when you look at that first homework problem, what is the thing that you notice about the data set itself?
I think it was the second one.
Oh, sorry, the second
Well, I noticed like there was like 307 repeated twice, and then there was two values out of the total of 12 that were below 300.
one. Okay.
That's what I noticed. So like there was like mode of 307. And is it mode that's supposed to be fine? I'm pretty sure.
And how did they feel distributed? Did they feel Gaussian distributed? Did they feel?
Off a glance, they kind of did,
Okay.
but I found out, I'm not gonna say.
Oh.
Well, we can have a discussion, right? Because I think the first thing that we want to talk about when we talk about today's work, we're going to be looking at this worked example of statistics. And the important part of what we're talking about today is the idea of how well do we understand the things that we can construct from the data? And what are the limitations to that? And then we'll talk about a way that if we have data itself and we fit a model to it, how can we be confident in our fit? And then we'll just be done. We'll finish up with the discussion of statistics right there. There's a whole section we can go into, which is called maximum likelihood estimators. But I think at this level of your life, you probably don't give a shit. And then we'll just go directly into tensors and gravity. So for today, thinking about that problem holistically, we want to think about not just what do the numbers say, what does the mode say, what does the mean say? But if these numbers are a real set of numbers, is there anything that looks unusual about them? And what are the warning indicators? If you look at a data set like this, that you think, okay, it's steeped in a physical meaning, right? Does this data point here give you pause, right? Like I said, 46, that's a pretty low weight. Now, maybe it does, maybe it doesn't. I don't really have a good estimation of 46 kilograms off the top of my head, but that's something like 100 pounds. What is 175 centimeters? That's probably something like larger than 6 feet. So maybe this was taken incorrectly. Maybe this had a broken scale, or someone accidentally added a foot, right? Do you have the actual height?
On 5 feet 8 inches.
Oh, actually, that's not bad. 5 feet 8 inches, okay.
And like,
This is 5 feet 8 inches.
I was just.
What about this one? 190?
Hold on. 6, like,
190 is 6.
6 something.
Okay, 190 is 6. So this would be 140. I mean, these all seem like skinny folk.
I mean,
Maybe
2 pounds.
it's 2.5.
75 kilograms is 165 pounds.
Okay, all right, a 6-foot person, 170. That's about reasonable. Maybe like a little lean for that height.
Zoom. I don't know, I've never done Zoom.
No, it's on Canvas. I don't know,
It's on Canvas.
like
It's on the left-hand side. It's the
Left
button called
hand
Zoom.
side
it has its own like.
button called Zoom.
Thanks, Trinity. We love you.
She can't hear you, she just can't find the Zoom link.
I know, but she'll see it in the recording when she inevitably watches this. Okay. So, okay, so we look at this data and one of the things that I want you to do with that first problem is to really, or sorry, the second problem, is to really look at the numbers and see if you can get a sense of them, right? Because when we take data, we talked about this a little bit in computational, right? There's always things like measurement errors, there's random noise, etc. And so generally speaking, you'll hear people say a phrase like, throw out that data point. Now, this is a slippery slope, right? Because some data, you can explain why that data needs to be removed, right? So for example, you take an image of a galaxy and you forgot to take off the lens cap. So you probably should throw away that data, right? Whereas if you take the data and you take an image of a galaxy and you see, one star that's very, very bright compared to other stars around it, that doesn't necessarily mean that you should throw it away, right? So you always have to have a little bit of like finesse. There's a little bit of an art to the data analysis. So that second problem, I do want you to actually look at that data look at it in as many ways as you feel are comfortable, whether it's, you know, sorting them by ascending order, whether it's plotting them, however you think will best help you understand what the underlying distribution will be there. Because if you just start with mean standard deviation, remember that we said, you know, you can have a very similar standard deviation and the distributions can look completely different, right? So reducing everything down to 2 numbers doesn't necessarily tell you everything about the data. Make sense? Okay. So let's do this worked example. There are 5 things that I want to know here. And this is going to lead me to things that I'm really curious about, which is finally one of this. Do we have the mean here? Yeah, last time.
Yeah.
I think I included in the comments.
Okay. And recalculate it.
All right,
I think the mean of y was.
Yeah, we can call this X and Y.
Mine's wrong because I have some average.
Oh, yeah, and then you have to divide by 10 or something.
And.
Something went wrong in the calculator.
it was simple.
Untrustworthy calculators.
the mean of y is 66.8. That should be the weight.
I'll do it. $75.7, so +26.
This one here?
Yeah.
You said 175.6?
Yeah.
Okay, that's fine.
Can't find the square thing. The square thing is the one that I had really wrong because it was really big or something. 'Cause that's the one I got from him.
Okay, so you did something like this.
But I just remember when I added up all of y squared, it was too big or something.
So you did the mean minus each of the data points, right? Quantity squared, and then you summed it. Okay,
I wrote down the equation wrong.
okay, let's write down the equation properly.
Well, I thought you said it was, the average of the x squared and then the x squared, the average squared. I didn't screw, not this.
Right, yeah, so that's perfectly good, so when you do,
I did this, the square all the y's and take the average, that I got like this, and that was wrong with me.
well, hold on a second, so this is,
Adding them all up squared, then dividing by 100. This.
I don't know if it's dividing by 100 here, so let's remember that, wait. So this is given to us on. Yeah, so you had your sum of y's was 668. Or are you just talking about the sum of y squared? 'Cause I had,
So much.
so I have something like 45,000.
That's what I got, but everyone else, they got something else that I got.
Well, so for s of y, it's that number divided by 10.
Yeah.
Okay, and then it's minus 668 over 10 quantity squared. And just to clarify this really quickly,
So 112.36.
112.36.
For S of Y.
Did you just grab it? So let's remember, hold on, let me write this down really quickly so you can see it here, because I think you might have a sign wrong. It's s squared equals x quantity squared, or sorry, x squared like this,
Oh, minus.
minus, yeah, x mean quantity squared. Which looks like, in practice, 1/n
So I
sum of xi squared minus 1/n sum of xi quantity squared. Oops. And another way of,
10.6.
yeah, 10.6.
Rewrite the equation.
What's that?
I have to rewrite the equation.
Okay.
S of X, I got 11.6.
Yep. Okay. So we were talking about how well we know these ones, right? And I told you it's not so simple to simply report, this is the mean of 175.6. Because in the real world, numbers have uncertainties, especially when they're derived from data. So even though we report something like, the acceleration due to the Earth's gravity is 9.8 meters per second squared, that's a lot, right? Because that is hiding the fact that this is not a given quantity everywhere in the world, right? So where is the gravity weaker?
At the top of the lake.
Good, yeah, you're farther away from the center. What's another example?
Gravity is weak other than being away from the source of gravity.
Mhm.
What, you gonna go in the middle?
What do you mean the middle?
I don't know.
Go to the corner.
No, if you go to the core. It is true that the gravity will become weaker as you go towards the core, because you're only drawn towards the material below you. But you'll be, on fire, magnet. Okay, so there is actually a place where your gravitational attraction is less than it is here.
Oh, a different planet.
No, on Earth, here, you don't have to leave the altitude from the surface. You just have to change your location.
Are you saying the Earth is lopsided?
I'm saying the Earth is doing something very specific that permits you to have a lower gravity at one location than in another.
That's great.
What? It's not fake. It's really not fake. And it's so not fake that we fly rockets out of these types of locations because we want to take advantage of this fact.
Is there something like the magnetic field pushes you away?
You don't need a magnetic field.
Okay, what is it?
It's the fact that the Earth is rotating. So if you are at the equator, you weigh less than if you're at the poles.
No, gravity should the same, it's just spinning, that's the.
No, but. it's-
Well, what does the spinning do? In a rotating reference frame,
That's a different force.
what do you mean that's a different
Is
force?
that like
Centripetal force?
yeah.
Yeah,
That's
so,
not the gravity, that's just you have a different.
But I didn't say gravity, I said the acceleration due to gravity, right?
Yeah, that's gravity.
Okay, you're right. To be very specific, gravity itself has not changed. But the acceleration due to gravity, just like as we moved up or down, right? If you were to like weigh the normal force, you would weigh less at the equator than you would at the North Pole. I apologize, that was a confusing question. And this is one of the reasons why we launch rockets out of Florida and Hawaii, islands that are near, I mean, not Hawaii, but they call it the Marshall Islands. The reason that you fly out of these locations is because they're closer to the equator. If you're close to the equator, you can take advantage of the fact that the Earth is rotating. Trying to launch from the North Pole would be much more expensive. Okay, so even when we report something like 9.8 meters per second squared, that's a lie, right? Because it doesn't account for these fluctuations. So it doesn't account for how high above sea level you are, what location you are on the planet. And so the question you always have to ask yourself is, well, that's probably a mean. In fact, that is a mean, right? And the question is, how well do we know that mean? And does the variation from a place like here in San Bernardino down to the equator, is that variation small enough that 9.8 is still a good number to use? Does that make sense? Because you'll see here that we have these numbers and we have an extra decimal place. And in either physics 1500 or physics 2500, you learned about how significant figures represent our confidence in the result. So we don't just go on and on and on and on, because these numbers down here are meaningless when you compare them to how well we know the question. So then the next question is, how well do we know the mean of X? I'm going to rewrite the form here and then we'll fill it in. So here's the mean of X. And when I use this little hat, we're saying that this is the estimator of that value. Okay. So generally speaking, we write it as such, X hat, not surprisingly. So that is the mean that you calculate, but now you have to report an uncertainty. Remember what that uncertainty is?
So they just or like sample population sample?
Yeah, right. So it's, in this case, we'll call it the sample standard deviation. That's S of X. But we're going to modify it here because we don't in fact know the true mean. So you have to add on this fun little factor, which is simply the square root of n minus 1. Okay, so here, how would you report that?
So for the mu of X, it'd be 175.6 plus or minus about 3.
You're the same? Okay, and what about?
66.8 plus or minus 55.
Okay. So this is a really interesting result, right? So what does this plus minus mean, this 3.9 plus minus? Does this mean that I'm gonna find 68% of my values within plus or minus 4?
If it is Gaussian,
I think the correct value is somewhere in that range.
Ah, okay, so this is what the plus minus means in this context. When I add plus minus here, I'm not saying anything about the underlying distribution. What I'm saying is this is the level of confidence to which we know this number. So it might be this number, but it might be 4 numbers larger than this or 4 numbers smaller than this. And it has no information about where the numbers that you derived this from are actually due. So what I mean by that is, if it were Gaussian, just like you thought, Orlando, they would be distributed within that, 1 sigma. But this is not a 1 sigma result. This is a confidence value inside of the mean. And that's a very subtle difference, but it's an important one to recognize. That make sense? Okay. All right, next one. Hmm. You sound.
I'm just copying, I'm sorry.
Oh, okay. All right. So we'll need one more value here. And this is one that I'm not gonna go through the derivation for. I'm just gonna show you what it is. So this is the variance in the standard deviation for. Let's see if I can throw too many things here at once. Yeah, I am, but it's okay. Yeah, same.
What's the curly V?
So these V's are, these are the central moments. We actually didn't talk about them. So remember when we were talking about, the first moment of a distribution is the mean. And then the second moment of the distribution is the standard deviation. And we said, well, when we subtract the mean from them, we think of them as central moments, right? So the second central moment here is of course just the standard deviation itself, the one that we just calculated. So if we're using X, I guess we're not necessarily, let me just write it like that. So that would be the standard deviation. But these other ones here, for example, that's the fourth moment of the distribution. And I'm not gonna make you calculate that. But let me just put them up here. They're written like this. I guess not more. It's probably a lot on on your calculator. It's just for you to do a quad like this. Right, I mean, that's not like an unbearable moment, but it's obviously not one that you just memorize off the top of your head. Okay, and then this is the same for Y. I'm just gonna do that actually. Can't be bothered. Okay. And for the definition of these uncertainties, so again, we will not just be reporting the uncertainty itself, that is to say the sample mean that we calculated over here. You know, that would be fine to first approximation. You say, oh, I've measured it and it's there permanently. You say, oh, the distribution in heights is 11.6 centimeters.
I just did, but she's not enrolled in the class, and she's not on campus. So she was asking me to send her a Zoom link like half an hour ago.
Okay, sorry, Trinity. I'm just telling the recording that she's definitely gonna watch.
Okay, I figured it out.
She's not on YouTube.
Oh, okay, you're right.
But she might not be able to find the YouTube link.
I'll send her the YouTube link.
Okay, if you don't mind sending her the YouTube link in the Slack, it's the same link every single time. Okay. So just to clarify this last point though, so you have something like n over n minus one. And you're gonna see this a lot. It's essentially a tax we pay for not knowing the mean. Okay. And I'm gonna multiply this here by s of x. Okay, and then I just can use this information up here, but I'm gonna take the square root of it. So it's the v expectation value sigma in the x direction. I would let you calculate that, but I don't want this to go too long in this discussion. No, it's not slow, it's just, computers are better at this, right? When you have when you use a spreadsheet, you put all the values in, it's really easy to just, copy and paste down the sums and, find the moments really quickly. So in fact, oops, I wrote that wrong. 12.2, plus minus 6.7. Is that surprising that the means are not the same? Sorry, let me say that again. Is it surprising that the sample standard deviation and what our expectation of the true standard deviation should be are not the same?
Yeah,
What does it make sense?
because of the sample variable, we're only limited to like those 10
Mhm.
points that we have.
Mhm.
And then, obviously, if we were to assume that we have like infinite numbers of data for the other one, for the sigma x, or for the variance, like we'll have to like work with the entire like scope of that infinite data, so like it's just accounting for like more points for that sigma.
Right.
This is what would replace the 3.9, right?
No, so this is a totally different number.
What are you asking us to compare it to? Is what
I'm asking you to compare this number. Right, so this is the sample standard deviation, the one that we get from the data, which is like if you clicked in Google Sheets and you say standard deviation of the data set, you get this number.
Yeah.
But it's actually not that smart. I mean, it's smarter than your cousin off of the street, but it's not smart in the context of how well do I understand the data set, right? So if you've never seen statistics before in your whole life, you say, oh, standard deviations, those look fancy. But if you have seen them before, you know that you simply cannot trust a single number. And let's look at the properties of this sample standard deviation, okay? So in the front here, as n gets really large, what does this value go to in the first term? Well, let's take n to be 1,000.
Yeah, so it'd be,
And
And that's basically,
that's like 1.6.
and the square root of 1 is. Good, so this number is basically s of x.
Okay.
So as my sample gets really, really large, then the original sample standard deviation is actually a pretty good approximation to the original standard deviation, right? But instead, this piece here penalizes us for not enough data points, right? Because what happens when n is 2?
Yeah,
So 2 over,
one,
and this is the square root of 2, which is
1.4.
how much? Yeah, 40% more, right? Than what you would assume. Can this ever be negative?
No.
No, not realistic. So this is basically a factor here, which is going to say whatever your sample standard deviation was that you picked, you're wrong, and you need to be less confident in your results, right? Because all this is gonna do is this is gonna inflate it. You saw that the maximum that it inflates it to, like you just said, is about 40%, and it goes downhill to 1, right? So it's a correction factor. And this piece here just represents what is the variability in the sample that exists, right? Okay, so 12.2 plus minus 6.7. Now maybe you got it straight on. Maybe the very first time you measured it, it was a perfect representation of the sample, and in fact, it was 11.6. Are these numbers inconsistent with one another? No, they're perfectly consistent with each other, right? Because this uncertainty here includes that value. Good, and that's by design, right? That'd be very weird if it wasn't. Okay. Does that process make sense? Yes?
Yeah.
Okay, all right, I'm gonna start deleting some stuff. And we're gonna talk about fitting.
that would be forever.
What?
I was looking at all the steps you have to take, and I always see like 5 years.
Well, again, I mean, so one thing that I was considering, and we can decide whether we wanna do this, is we could do next, or this Wednesday's class. In the computer lab and pull some computers out, and I show you how doing it on your calculator is obviously garbage and not very fun. Because you can make mistakes, but if I give you a sample data set, you could just, using Excel or using Google Sheets, you just, pull down these tabs and they instantly populate. And particularly when we're about to talk about with line fitting, this can be a very valuable tool, because what you can do is you can take a random data set, you can apply a random model to it and be like, this model is worse than this model, right?
I think that'd be nice, because I was trying to use Excel the other day and it really was good.
Okay, then 50% of the class, 100% of the class, 100% of the class, we'll do, whoa, unanimous consent. We're gonna do a class on Wednesday then, which will actually be, well, I'll make some simulated data sets and we'll try and,
Give us real data.
what kind of real data? You want spectroscopic data? Oh, God, no, I'm not gonna do that. I mean, maybe I'll do that, we'll see. Okay, okay, we're good with this for now? Yes, we're gonna skip ahead to something called the method of least squares. Have you heard this before?
Yeah.
Okay, so what does this mean to you, Rolando?
Method of least squares, isn't it like you just like, it's like a line fitting where you have like you plot the data.
Mhm.
You plot it and then you try to find like a straight line that like goes through most data points or like aligns with most of them, and it kind of like shortens like the length in between like that line. Like from that dot to that line, and does it for like all the points.
Right, right. Yeah, so that's a great introduction. So what we're doing in the context of method of least squares, just like Rolando said, is that we're trying to find something that goes through the data points. Well, so the data points are scattered in some unknown way, and the versions that we'll talk about today will start with a line, like you mentioned before. But there aren't, it's generalized. There aren't issues with, say, taking a more obscure model and applying similar techniques to it. Okay. We're gonna delete half of this right now. Come back to it. So. You need to have some data set, and this data set needs to be a paired data set. So we're gonna say something along the context of xi, y. Okay, I can be 1, 2, 3, 4, etc., all the way up to n. So the example they talk about in the book is temperatures along some metal rod, right? Various points. Okay. So let's imagine rod like this. And for the purposes of this example and or intellectual discussion, let's imagine that we place small electrodes or thermometers or whatever you want to measure here. And we're gonna assume that the measurement uncertainty only exists in y. So what that means is that whatever, you had an arbitrarily precise ruler. And as you went along, you measured out the locations of all of these little points. And so therefore there is no uncertainty in the x value. Okay. Okay, so here's the fundamental theorem of the method of least squares, and it's fairly straightforward. All it says is that for every value of yi, you have some function, so we'll call it f of xi, given the key parameters that we talked about. Oh, that looks like a J. It's just semicolon. So remember, think it was last week, we talked about the idea of some underlying distribution with parameters A. These are the parameters. And we're gonna see an example of this really soon, so don't get bogged down in the details. But the important point is there is some unknown noise. There is some form of experimental uncertainty. Does that make sense? Okay. Usually you can assume that that type of noise is either Poisson or Gaussian, depending on most common types of noise. But it'll be very different from object to object. Okay, so this leads you to something fairly straightforward, which is something called the chi-squared statistic. You've seen this before? Yep. Okay. Chi-squared of A is going to be the sum of all of your yi's minus the function and the parameters, whatever they are, all over the measurement uncertainties for this value, quantity squared. Okay, helpful or not? Kind of obscure, like what are you doing with it, right? Okay, so we can look at various forms of an F, right? But essentially what we're thinking about is, let's take a data set. X, Y. And there are uncertainties. Alright. Maybe I should have drawn uncertainties first. Okay. So here is our values. That uncertainties, sorry, that's. And you know, I could imagine, well, that looks like maybe there's some curvature in there. Right? So maybe I want to take a line and have it start up here. Maybe go down and then up and then down and then up and then down and then up and then down. I could get through every single point, right? So if I had something like how many points do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 points. So what level polynomial do I need to fit those?
9. Alright. I'm just guessing numbers.
Okay, so let's start with the easiest one. I have two points. How do I fit them?
Like,
Oh,
1, okay, good. If I have 3 points, I need 2. Isn't that true? Isn't that the definition of a parabola? Let's have a look.
yeah,
Well, you just said yes, but let's make sure.
okay.
No, thank you. No, like learn on Monday. What?
Yeah, so 8.
well, like,
8?
Yeah.
Yeah, it's n minus 1.
Cool.
So you could absolutely fit them perfectly with n minus 1, right? But is that the right way to do it?
Yeah, overfitting.
Yes, exactly. Okay, so that's a term that we'll get to in a little bit called overfitting. But in particular, okay, let me just draw a picture because I just erased it. So here's a point here, and here's a point here, and of course I can draw a line through it. But if I put a third point over here, now I could still draw a line through it, right? I could go like that.
That's not very.
Maybe, maybe not, depends on how big the error bar is, right? I could do this too, wee, perfect. Right? But if the error bars look like this,
Oh, then the line.
then you'd say, well, which of those are you most confident in? What's that?
It looks very, very.
It looks very vague, right? It could be either. So in particular, what we'll look at today, we have some examples and, we won't have enough time probably to get through all of the different ways of thinking about these, tests. But when it comes to understanding statistics or understanding the data itself, simpler tends to be easier. And as you'll see, this type of work using a chi-square test for parameters A, and this is some vector of parameters. If you have a longer vector of parameters, there will be uncertainties and there'll be correlated uncertainties between them. So if, for example, you look at straight line that goes through these points, right? Then you have two parameters. Because I could fit the point like that, or I could lower the y equals mx plus b, and I could tilt it like that. So there's correlation between the first parameter, which is the slope, and the intercepts, right? As opposed to this one, which is curved like that, and this can move up and down, or it can twist this way, right? So there's three parameters when it comes to this one, and they're more correlated, right? Okay. So generally speaking, the rule is you could fit endpoints with n-1 polynomial. But it okay. So if I look at the data set that I created, what do you see generally speaking? Yeah, a line looks like it would fit perfectly well. Where would you draw that line?
I like getting up.
Just tell me where you do it first and then.
I probably do it through like this one because it's the smallest error bar. You try to think it's something you can find and fits like most of like you can't fit it out. Start from here. Yeah, no,
That's close.
yeah,
That's close.
I guess you could make it a little curved.
No, you don't have to, because we want to start to see how good it is. As a function of not curving.
I think it's pretty
So
good.
that's pretty good, right? I mean, I got through a lot of the points, just barely clipped some of them. And we want to really think about what this process is doing here. So the chi-square statistic, remember that the word statistic is something that we construct about the data to tell us about how good or poorly we're understanding the material. So what does this thing do? So this takes the real data points and takes the difference between them and a model. And it compares it to the uncertainty at that location. Okay, so then you take the sum. So if the uncertainties are large, is that a more or less valuable point to your sum? Less. Because you're subtracting by a larger number, right?
Does
Quantity
the chi-square
squared.
tell you how, would you say how important it is?
We haven't exactly discussed what it does yet.
Mm-hmm.
So I'm gonna show you, it's okay, no, you're almost there, right? You're anticipating the question, which is you start with this data. You have properties of the data and the model you're using, and we're saying, well, what does this thing do? Right? So this is clearly some number. I haven't told you what the number means yet. But let's think about it in the context of, let's say it goes through the center of every single point, so that they're spot on. Okay, then what would this top part be?
It have to be zero.
It has to be 0. Right?
Goes through every single point, the chi-square would be 0.
If it goes everything will point through the center, it did not from the error bar.
Look at that. Boom.
And,
Chi-square by definition is 0.
Point times the function tells you,
The function is whatever function that we're creating,
okay.
right? So if I draw this up here,
That's why it has to be 0.
what's that?
That's why it has to be 0.
Yeah, that's why by definition it was 0. So for here, for this point here, right, so this would be the y of I, and then this would be the location of f of xi comma a, right? And that would be the difference between them, minus here, right? Okay, so let's look at just this piece here. So what is this contribution to chi-squared?
The classes in here.
What's that?
And so, yeah, it would be above the number, because y is origin and the other x.
Does it matter?
No, that's squared.
It's squared, so it doesn't matter.
That's true.
So look at it one more there's one more thing that I haven't drawn in there that I'm hoping that you sort of see. You're definitely looking at the top, that's very good. What does the bottom tell us?
That's not the variance.
It's not the variance, right?
It's the standard deviation.
It's neither the standard deviation nor the variance. This is the measurement. Uncertainty.
To the error bar,
Exactly.
so it has a big error bar.
Good. So there is a big difference here, right? Like this is a, kind of substantial difference. But it's also occurring with an object whose uncertainty is large. So its individual contribution to chi-square is greater than, less than, or equal to 1.
Probably about 1, but that's just guessing. Wait, 1?
I don't know, you tell me. You can look at it and you can tell me, I promise you.
You're probably like a little bit less than 1.
A little bit less than 1, right? Because this number here, this minus this, is smaller than this.
Yeah.
So that means the top part is smaller than the bottom, so therefore it's a number smaller than 1, and then I square it. So it's a number certainly smaller than 1, right? That makes sense? Okay. So let's do another example here. What about this guy? So this one here is your yi, and this one here is your f of xi comma a. Yeah, certainly it looks greater than 1, good. And by how much would you imagine?
Yeah, it looks like the error bar is like about a third of the length.
Good, okay, so I would guesstimate that as well.
3.
So 3, and then,
Oh, 9.
very good. Okay, so this one contributes something like 9. Right? Okay, so
10.
what?
We got 10.
We got 10, okay, so that's 2 of the points. How many points did we say there were?
9.
There are 9. There are 1, 2, 3, 4, 5, 6, 7, 8, 9. So for numbers where you go through the error bars, you get numbers that are less than 1. Right? And for numbers that you don't go through the error bars, you get numbers greater than 1. And for numbers that you go directly through the point, you get almost close to 0. So look at these points here. So maybe I got 1 here. That seems pretty reasonable. This is a number less than 1. That's probably 1. We just said that's number less than 1. That's probably 1. That's probably 0. This one's pretty close to 0. And this one's pretty close to 0. Okay, so 0, 0, 0. 1, 2, 3. 3 in a little bit. 4. And this number here is 9.
13.
13. Okay, so what did we actually do? Well, you just said a bunch of numbers in a row, Krismani. I have no idea what you actually did. This is a measurement of how well does your model represent the data. And you are really using this in order to compare it to other hypotheses. So the null hypothesis, which is the thing that all scientists are required to start with, is that there is no correlation at all. What would that look like?
Big number?
How would I plot no correlation?
Oh. Like you would just draw a line on top like a rainbow?
No, because that has curvature. So that must be a two value parameter, right?
Wait, you
Oh.
want a function that doesn't correlate with the data at all, or what are you saying?
So let me ask you this question, right? So if we're doing science, and in particular, we're looking at a rod. Right, so all of these values are values along the rod where I'm heating it up. Okay. And you are trying to tell me that the line model, one that increases with length, is the one that will accurately represent the temperatures. And I respond with, no, I think they're uncorrelated. So you pitch to me y equals mx plus b, and I respond with,
Y equals negative evidence to speak?
that would be uncorrelated.
They wanted.
Sorry. Let me say that again. That would be anti-correlated.
Oh,
Uncorrelated, you would probably,
then draw the rainbow. Like-
A rainbow would be correlation with a quadratic function.
uncorrelated, well, like, y would have to equal like some function that doesn't involve x.
Some function that doesn't involve x.
Yeah.
What does that look like?
F of Q.
F
Y
of
is
what?
the-
Q, f of q. Yeah, so something like this.
Or rainbow.
No, because if it has curvature, if it changes with x, then it depends on x. It has to be a constant, right? So this would be some constant, right? Q. Okay, so your first job is to demonstrate that your model, in fact, does better than a flat line that does not depend on the value that you're changing, right? So let's see if that's true. Now I chose a super arbitrary one, right?
Q.
But, I mean, let's look at it. I mean, just you can do something called chi by eye. This is a data analysis technique where you look at it and you say, did that represent the data well?
No,
No, really, it doesn't. And I can move it down maybe to hit a few of them. To maybe grab this one. So this would be contributing 1 and this would be contributing 1. This is less than 1 now, right? So this is 2. This is basically 0. This is 2 and a little bit. So maybe let's get up to 3 at this point. This guy's way outside.
Yeah.
So this is probably 4. So now we're up to 6. This is not so bad. So this is maybe like 6 and some change. This one's rough. This
So
one's
we
really
have
good.
it square the 4, maybe 16.
right, you just-
Well, I was gonna use 2. I just imagine that was,
Oh,
oh, you're right, this might be 3. Okay, so let's go back. That's 1, 2, 3. Yeah, that's about 3. So that would be 9 as well. So this is a 9. It's probably more than a 9, maybe a 16.
Yeah.
This thing is like a
That could be your.
That could be a 4. Okay, so that's like a 29 just from these 3 points. Right? So boom, you've already sunk the first model. That there isn't a correlation between the 2 data points. You see?
Yeah,
Okay, but that's the first test we have to do. That's the null hypothesis testing. So now with your second one, you could say something like, well, okay, now we draw this beautiful line through it and we're comparing them. But let's say Isabel comes along and she has a really good eye and she says, actually, I think it's more like this. Right? And she wants to take the penalty here for the increased cost saving there. Right? So what you can do here is you can compare different parameters, even still within a line. Right? You can say, well, I think the slope is slightly shallower, and maybe this one gives a chi-squared of, what did we say it was, 14?
13.
13, okay, but this one gives a chi-squared of 11.
yeah.
I'm not saying I didn't actually calculate, but let's say that that was
Yeah,
the case, right? Chi-squared is a statistic that allows us to show some value of confidence in the technique that we're using, right? Okay. So you might be thinking to yourself, well, because money, well then, you just keep adding polynomials and you should win out, right? In fact, that's not how the chi-squared statistic works. For every new parameter that you add, you get a penalty. So as you add more and more parameters, your chi-square, like for example, comparing a straight line to a constant can't be done 1-to-1. Because you're gonna need to add some extra information to the fact that you've now added the parameter. So there are tables that you'll find online. I don't know if there's one in this book. There might be one in BOAS. Where you just look at how many data points you have, your n, and then you look at different values of chi-squared.
Yeah, I have that book on me.
Do you really?
Yeah.
That's perfect.
I remember Dr. Floyd had seen something.
Yeah, I don't think it's in this one.
I'm sorry.
No, it's okay, no, I'm curious,
If you know where it is, you look.
I do not.
Oh, that's a funny book too.
So funny. I forgot, wasn't there a story for the front?
It's true, that's a true picture.
Yeah, I forgot what happened, but it's like, it did some bad error analysis.
Yeah, it just drove it.
People don't even know where it is.
Yeah, sure.
All right, did I just find it? I think I just found it.
Good job, Rolando.
Did that?
Okay, so you have it here, probabilities for chi-squared, and in fact, we have it here, right? So, you'll notice that this is it's called the reduced chi-squared. There's different ways of talking about it. Reduced chi-squared just means that you are taking into account how many degrees of freedom, how many data points you have. Like, so let's see if I can just do that really quickly. Here's your chi-square. You'll notice that it's a sum. The most, or sorry, for each one of these values divided by their uncertainties, they could all contribute something that is between, 0 and a large number. But mostly they'll be contributing, if it's a good model, something around 1. Right? So as you add up the number of data points you have, if you then divide by the number of data points you have, you then get 1. So a reduced chi-squared sometimes can just tell you off the bat that, okay, if it's greater or less than 1, then your data either is good, right? It fits the model quite well, or the model's not really quite right, or the uncertainties are too large. So what do I mean by that? If your reduced chi-square is greater than 1, but not that much greater than 1, you probably have a good model. If your data is, or your reduced chi-square is exactly equal to 1, that's really impressive. I don't know how you did that. If your reduced chi-square is much less than 1, then your uncertainties are probably overestimated. Okay? Now, degrees of freedom is not exactly only data points, it's data points and how many parameters you have in your model. But that's something that you can get into at the back here. But as you'll see here, you have the number of degrees of freedom. Here's B, and it's a table that goes out. And then you have values for, wait. So these are your values for chi-square, and these are your values for degree of freedom. So, let's see, what? This is like a finer detail one. It goes between 0 and 3, and then this one goes from 0 to 10. And usually the chi-square is telling you, the reduced chi-square tells you the probability of obtaining a function with that many degrees of freedom based on the data that you have. So these are always measurements. These are always measurements of how confident you are in the choice of model that you've made, given the number of parameters that you have. There are other criteria as well. So there's something called something with an A, it's either the able or the Akatori criterion choice. So what it does is it says, right, because we construct these, and I told you that statistics are created by humans, obviously, not handed down to us from on high, you can always construct them so that they penalize you for using, too many parameters in your polynomial fit, or by constructing too complicated a method when something simpler might do. And so there are statistics that you can find out there that characterize how well do you understand the data, given how many parameters you choose and the uncertainties in the model itself. This one here doesn't quite care, you can't see it yet, doesn't quite care how many parameters you use. But it's great for a single set of parameters when you're comparing between two models of the same type with the same number of parameters, right? Okay, so chi-square is not the end-all be-all statistic, and in general, if you just quote a chi-square or a reduced chi-square, that should be fine for your scientific paper, especially if you give the number of degrees of freedom. But people, when you go to submit your first publication and you add your chi-square, they will still yell at you for things that you didn't even know you didn't know, right? Okay. This is the linear square fit that we were talking about before. Generally speaking, you can run it through a nonlinear fit. We won't talk about that here, but you could imagine, and maybe we'll do this. Yeah, I guess we should just do this in person on Wednesday. So if you have some data like this, and even if you just have 10 data points, right, you can imagine you have some slope like this, and you just keep changing the slope, right? And you look for where the slope was the greatest. And you will have two parameters, like we said, they'll be correlated. So you're going to have some parameter space, right? And it'll be a table like this. And on one side, you'll have M, and on the other side, you'll have B, right? And let's say this goes from 0 to, 5 or something, and this goes from 0 to 3, and you can bin it up however you want. Okay? All of these are bins, and then you just calculate in each one chi-squared, right? And then when you plot it, you'll see a shape. Because you will see over here, you have very high chi-squares, and close to the region where you have good agreement with the data, you will have a valley. So down here, you will have the lowest chi-squares, right? And there's some more analysis probably that we won't do that looks at both the width and the height of a parameter space like that. Sometimes they're not correlated at all, and it's just a perfect circle. And that tells you a little bit about the uncertainty in the parameters that you just fit. Does that make sense? And there's many ways to do this type of work. We'll do it the bulk. We'll just, we won't do anything sophisticated. We'll just create a plot like this and you'll see the data and you're like, oh, I get it. Whereas there are much more sophisticated techniques that use the fact that there is a valley. And just like someone who is skiing would try to find the shortest path down by just going down the steepest descent, you could do that with what's called the Levenberg-Marquardt model, which would start at a location over here and just find the slowest, the lowest, the fastest way to the lowest point. Okay, questions about chi-squared?
What was your definition for chi-squared again? I wanted to-
Measurement of how well your function fits the data.
Yeah, more or less. It's a statistic. It's a statistic of how well your function fits the data. And like all statistics, it requires interpretation, right? Okay. So we could talk about some different statistical tests like the p-test and the generalized like likelihood ratio. But I think, I don't know, I'm kind of feeling like I'll show you some data analysis stuff and then we'll just kind of be done with the statistics part. Does that seem reasonable?
Yes.
Okay. So that means that I would love for you to jump into so which I don't know if it's in. Okay, it won't be in the same part of this book as it will be in the BOAS book, but you should start brushing up on tensors. Now you saw tensors in fluid dynamics and you might have hated them. So we're going to learn how to deal with them and we're going to apply them to GI. Gravity. Okay, any other questions? Bagel? Mr. Bagel this morning. Okay, thanks, folks.
Thank you. Bye.
Hi.